Alright, so we have this frame that consists of rod A, B, C, and is connected through rod BD through a pin joint at point B. The ends of the frame are connected to a sort of rigid wall and floor through pin joints A and D, and I have a load acting at point C. We're going to assume this frame, or the weight of this frame, is negligible compared to the applied load here. And here's my question for you. In which direction does the pin joint here at point A, which direction does it push or pull on the frame? And here I'll give you some choices. Does the pin joint push up on the frame? Or does it pull down? Does the pin pull to the left? Or does it push to the right? Or maybe it works in a combination of directions. It can go up and to the left, up and to the right, down and to the left, or down and to the right. Or maybe, just maybe, it doesn't have any force at all. And here you might note that this is a statics problem, not a dynamics problem. And you might be asking, why are we doing the statics problem here in dynamics? And the reason is because it highlights a type of thinking that I want to develop in dynamics. A type of thinking of how to approach qualitative problems. Notice that I didn't ask you how big this force was, right? I didn't ask how many newtons was that force here at pin A. I just asked a qualitative question. Which direction is it in? To answer this question, you might be inclined to use your gut instinct, your intuition. You might be able to say, I can just sort of picture this in my mind's eye and see that it acts up and to the right or down and to the left, or maybe you have a good intuition that'll tell you what the answer is. But that's not what I want you to do in this problem. What I want you to do is I want you to analyze this thing rigorously using physical principles. But I do not want you to do it mathematically. In other words, I want you to answer this using something I call analysis without equations. That is, we're not going to set up equations for equilibrium. We're not going to be solving for things directly mathematically in that usual mathematical sense. But we are going to do it qualitatively. So let me show you what I mean. Now, the first thing I'm going to do in this analysis, just like a lot of my sort of mechanics analysis, is draw a free body diagram. I'm going to do a free body diagram of this entire frame. The first thing I'm going to note is that I have a force here pulling down. So I'll indicate that right there. And I'll call that force L for the load acting on the frame. Now let me scroll up just a little bit. At the pin joint here, this is what I'm after. There's some force pulling up, pushing up on this thing, or maybe pushing down, or maybe pulling to the left or to the right. I'm not exactly sure yet. But there's some force over here doing something, right? Something like that. Now to represent this force, I'm going to split it into its horizontal and vertical components. So rather than writing it some general force like this, I'll write it as a force with two components. A component I'll call AX in the horizontal direction or the I direction, and an AY in the vertical or the J hat direction. But I don't know whether this is in the positive I hat direction. So maybe I'll put a little tiny question mark there. And if I don't, and also I don't know if this vertical piece is upward or downward. So I'll put another question mark right there. And that's what I'm asked to find. And likewise at pin D, we've got a force acting over on the frame from over here. And which direction is that? I'm not quite sure, but I'm just going to sort of put it here. And again, if I split this one into components, I can approach it in a very similar way. That is, I can write this force at the pin joint at point D as some dx in the I hat direction, dy in the j hat direction. Again, a priori, at the very beginning here, I don't know which direction that is in. I don't know whether it's actually pushing up or pulling down. I don't know whether, at least rigorously yet, whether this one's pushing to the left or pulling to the right. But nonetheless, here's my free body diagram. Now, when solving mechanics problems, even if we're not using mathematics to solve our mechanics problems, it's good to sort of take stock of what is unknown and what is known. So unknowns, if we were to list them out, would be the AX, the AY, the DX, and the DY. In other words, we would have 4 of these unknowns. But what sort of equations could we get to solve for these unknowns? I know I'm not asking you to construct equations, but what if you were to? You would take the sum of the forces and add all those up to 0. And when we do that, what are we doing? This is the equation for static equilibrium, or one of the equations for static equilibrium. And when we do that, what do we get? We can split that into horizontal and vertical pieces. So for example, we can take the horizontal piece of this, and so let's say all the horizontal forces add up to 0, and then we can do the same thing for the vertical pieces and say they have to add up to 0, and we get 2 equations out of that, right? And then we can do a moment equation, take moments about any point. I'll just say point P, and point P is someplace on here. sum up all those moments, and that also has to be 0. So we get sort of moments going clockwise, counterclockwise, whatever. We get another equation. So add those two up, we get 3 equations, and we just have 4 unknowns. You might say we take a moment about some other point, but you may recall from your statics class you can only get 3 equations out of this. If you take a moment about some other point, you just get another equation, but it's dependent upon the other 3, so it really doesn't help. In fact, it doesn't have to be 2 force equations and 1 moment equations. It could be 2 moment equations and 1 force equation. But 3 is the most you can get from a 2-dimensional type problem. So what we have here we have too many unknowns for the amount of information we can get from a 2D statics problem. So somehow we need to figure out how to resolve this. So what I'm going to do, actually, I'm just move this stuff out of the way. And the way we're going to get out this is we're going to look at just this member right here, BD. We're going to check out and see what it's doing. So here I'm drawing a free body diagram just for member BD. And what sort of forces are acting on this thing? Well, I've got force at D again, and I'm not sure which way I'm going to draw this. I'll just draw it this way. I'm going to not put it into its components as I did down there, but I got some force acting on point D. In fact, I'll just call this vector D. And this member also has a force acting at point B, right? And I'll call this one force B. And these are the only 2 forces acting on the member, right? We're neglecting the weight of the frame. In fact, we're neglecting the weight of all parts of the frame. So we're not going to put any weight on member BD here. And the thing to note that this member BD, this is a 2-force member, right? There's only 2 forces acting on this thing. And when we have just two forces acting on something, some rather special things occur. So for example, if I take all my forces acting on this body and set that equal to 0, what do I have? My only 2 forces are these 2 forces B and D, and they have to add up to 0. I know I said I was going to do analysis without equations. I'm not doing this. I'm not constructing these equations with the intent to solve them. I'm just constructing these equations to express an idea. I need these 2 vectors, B and D, to add up to 0, right? And there's no way that these 2 vectors, at least as I've drawn them, are going to add up to 0. There's no way that this one's going to exactly cancel that one because they're going off in totally different directions, right? The only way that I can have a force B which cancels vector D is if they go in opposite directions. Exactly opposite directions. In other words, instead of having B go up and to the left kind of like this, I need it to go in exactly the opposite direction of point D, and I need it to have the exact same magnitude, right? They have to be exactly opposite of each other in order to have equilibrium. And furthermore, remember that I need my moments to add up to 0. So if I take moments about any point on the body, even off the body, it has to add up to 0. So in particular, what if I take moments about this point right here? Well, D is going to create a moment about that thing, right? So I can't have D acting that way. D has to push or pull on this rod at the other end of the rod in a way that creates a 0 moment about point B there. So therefore, D cannot be going sort of up and to the right like that. It has to act through that point I'm taking moments about. So in other words, D, instead of being like this, it would have to be more like this over here, right? D would have to act that way in order to not create a moment about point B. And then likewise, since I need my forces to add up to 0, force at pin joint B would have to go the exact opposite way. So in other words, these two forces would have to be collinear, right? Acting along the exact same line. And they can be collinear as I've drawn them in this way, sort of pulling this rod apart, pushing making this rod in tension. That's perfectly fine. That would create a 0 net force and a 0 net moment. Or of course, for a 2-force body, they can also go directly inward as well. But the important point is that these 2 forces have to act through those endpoints on the body. They have to be collinear. Aha. So now if I go back to my free body diagram over here and look at the force at D, I cannot have anything in the vertical direction, right? That would be sort of perpendicular to rod BD. Can't have that. So therefore this goes away. Now if I count unknowns on this full frame, I've got 1, 2, 3, right? AX, AY, and DX. And now this problem is solvable, even though I'm not going to actually solve equations here. Okay, now I know I have the right number of unknowns at least. Number of things I need to find, right? In particular, I want to find this AX and AY, whether they're pushing to the left or to the right or up or down. All right, so now that I've revised my free body diagram for the entire frame, let me start doing some analysis. Analysis without equations. So first thing I'm going to do is I'm going to look at the moments about point A. Why am I going to do that? That's a really important question. So let me just write this down. You take the moments about point A, that has to be 0, right? That's an equilibrium principle. It's an equilibrium principle that I've written as an equation, but I'm not going to treat it as an equation. Right now, the equation is just an idea, right? It just says the moments about point A is 0. I'm not going to actually set up equations of motion here. What I'm going to do instead is create a table. On the left side of the table, I'm going to list the forces, right? All the forces acting on my body. And on the right side, I'm going to list the moments about point A, at least qualitatively. So my forces, I'm going to put them in some sort of order. So I'll start with AX, AY, L, and DX. DX is in the I direction, like so. And then when I list their moments about point A, so does AX make any moment about point A? The answer is no. AY, again, it acts through point A. Again, that makes no moment about point A. L, what kind of moment is that? Well, it's going to create a clockwise moment about point A, right? So to indicate that clockwise moment, again, we're just sort of doing qualitative problem solving here, not actually calculating any numbers, but we're going to say that that creates a moment clockwise, right? Sort of a right-handed turn, if you will. Now dx, at least is the way I've drawn it right here, if dx is pushing to the or pulling to the right, then this one also makes a clockwise moment. And that's a problem. You see, these moments all have to add up to 0. So I've got the 0 moment, clockwise moment, plus a clockwise moment. That's going to give me a net clockwise moment, and that cannot happen. Right? So that tells me something's wrong here. And L is going straight down. It has to have a clockwise moment, but the dx, I didn't know which way it pushed or pulled. The dx, I drew it to the right, but obviously it's not to the right, because if dx was to the right, then it would create this clockwise moment, which would not balance all the moments out. So that cannot happen. So what I need is for dx to go the opposite direction. So instead of having dx pull to the right, I need dx to be pushing to the left that way. And when dx pushes to the left, then it creates a counterclockwise moment down here. Right? We get a moment going the other way, and then this all checks out. So dx has to be to the left in order for the moments about point A to go away. Interesting, huh? We did not solve any equations whatsoever. At least we didn't solve anything symbolically. We just looked at which way these forces have to go in order to make this moment equilibrium condition satisfied. So that I know that this sort of scalar component of my d vector, I'll call it dx, has to be negative. Essentially, so this d vector has to go to the left. Let me work on some other equilibrium conditions. In particular, what we'll do is we'll look at all the forces, add them all up. They have to equal 0 now, right? That's the 0 vector. And again, what we'll do is we'll make a table. We'll put lists of all the forces here, and we'll look at the I hat, or the horizontal components, and we'll look at the j hat, or vertical components of these forces. So here I have the forces listed, L, D, AX, and AY. And let's look at the horizontal pieces first. So L is perfectly downward. It's vertical. So there is no horizontal piece here. D does have a horizontal piece. It is to the left, right? We've determined that already from that previous part of our analysis, looking at the moment equation looking at the moment equilibrium condition about point A. So D we know is to the left. AX, again, this had a question mark on it, so we don't know whether it goes to the left or to the right. That's part of what we need to determine. But I've drawn it to the right, so let me just put it to the right here. And then AY, that's perfectly vertical, so that goes to 0. So what do I have? I've got an equilibrium condition. And at least if I look at the horizontal component of the equilibrium condition, some of the forces have to equal 0, so some of the horizontal components have to add up to 0. So since the D is pushing to the left, the AX has to be pushing to the right. In other words, when we drew this, we got the direction correct, right? When we did our first guess here. These two forces have to add up to 0. They have to exactly cancel each other out. The only things that can cancel each other, the only thing that can cancel the D pulling to the left is this AX pushing to the right. So we know that AX has to be to the right. So let me go down here, I think, and take off this question mark. We know that AX has to be pushing to the right. In other words, AX has to be positive. Yes, that's a nice result, actually, because that partially answers our question up here. Which direction does the pin joint A push or pull on the frame? We know that pin joint A pushes to the right. We don't know yet whether it goes up or down, but it's definitely pushing to the right. So let's go address that up and down question. Let's go to the vertical component of this force equilibrium condition here. Again, L is straight down. So if I were to write that into my equilibrium table here, right here, this thing's going straight down. D is pushing exactly to the left, so that does not have any component in the vertical direction. AX, again, it doesn't have any component in the vertical direction either, so that's a 0. And then AY, at least as I've drawn it, is going upward, right? So AY is going upward, L is going downward. These are the only 4 forces acting on the system. The L and AY are the only 2 acting vertically. So these vertical components have to exactly cancel each other out. So therefore, AY has to be upward. So in other words, AY has to be positive. So again, get rid of this question mark over here. We know that AY is positive, just like I've drawn it. And therefore, this force AY acting on our system has to be to the right and upward. So the answer to our question, let me just go back up here. In which direction does the pin joint push or pull on the frame? It pushes to the right and upward. And that's our answer. Done. Again, this is done without any equations at all. We didn't have to solve for anything mathematically, but we went through what those equilibrium conditions mean. And going through that, we can determine rigorously that the pin joint acts upward and to the right at point A on the frame. Of course, there's another way of doing this called using the idea of a 3-force member, and there's some nice conditions associated with that. I'll let you try that or look that up sometime. But here's how we went through the equilibrium conditions one by one and got it. I kind of like this. All right, we're done.